Good morning, everybody. Thanks for joining us. I see we're still waiting on quite a few people. I'm going to give it about one more minute and then we'll kick off. Okay, thanks again for joining us this morning. Welcome to our fourth workshop on RETScreen Expert. Today we're talking about modeling HVAC, and this is actually part one of a two-part series on this same topic. We're joined by Stephen Dixon, a familiar face, and a special guest today, Michelle Perrant from TechnoSim, who has, like Stephen, over 30 years of experience in the energy efficiency industry. Our second session on this topic is taking place November 12th. If you haven't registered, I'm putting the link in the chat right now, so you can do so. The second one is going to be longer. It's going to be a 2-hour session, and we will provide everybody a temporary 14-day RETScreen license that you can use to follow along in the workshop. So with that, I'm going to pass it over to Stephen to walk us through the agenda.
Great. Thank you, Megan. Welcome, everybody. So this session will be sort of a show and tell session, and then the next session is going to be hands-on. So don't worry if, as we're going through today, that it's a bit quick and maybe you were trying to follow what we're doing in RETScreen. We will give you a 2-hour session the next time where you'll actually be able to follow through, and we'll probably use exactly the same examples, but you will then be using the keyboard and working with it. We'll assign you maybe answer a question, determine a value, or something like that. So we want to make it as real and as skill developing as possible. So for today, what we're going to do, well, we've done our welcome introductions. I'll give you a quick overview of RETScreen Expert. I mean, we always do these at the beginning. For some of you, it may be new. For some of you, it may be a little bit of a review, so apologize for that. Following that, then I'll talk about basically how to model HVAC systems at a high level. So what are the different elements that we have to deal with in an HVAC system, the heating, cooling, and the air handling system, the ventilation model. So we'll kind of look at that. I've got an overarching example, a fairly simple one of a constant volume system modeling a rooftop unit. And then Michelle will walk into a number of different examples. So we'll take a look at, I think, 5 or 6 different examples or circumstances where we have to basically model an HVAC system, you know, a makeup air unit, an exhaust system, a VAV system, a constant volume. And he'll talk to us about how best to use RETScreen to do that. So RETScreen is a really good calculating program. It has some relatively simple models for being able to basically get to an answer in a reasonable amount of time with reasonable accuracy, but we have to use it properly. So what our focus in this session is making sure that we're using these models in the best way possible. And so we'll present you with some results and solutions, which will be the sort of the answers to the assignments next week, and also some cautions to avoid poor results. So the idea here is to improve the way we use the HVAC models in RETScreen in a way that we get a much, much better building model. And then we'll wrap up with Q&A, but I think we always like to take questions as we go. So I think Megan will be watching the chat. If there is a question that comes up as we move through it, that we'll certainly try to address that if possible. We only have an hour, but we'll do our best. So just a very quick overview of RETScreen Expert. It is a pretty widely used tool across the world. Excuse me, and in many, many different languages. I like to say that it's an all-in-one toolbox because it does contain tools and functions to allow us to do benchmarking, feasibility analysis, performance analysis, and actually portfolio analysis where we wrap it all together. So today what we're going to be focusing on is actually the energy calculations in the feasibility analysis. Now, suffice it to say that when we do the energy calculation in feasibility, we get basically a cost reduction calculation if we put our prices of energy in, and also the emission reduction calculation. So really we're going to be focusing on that. The first element of that green piece under the Smart Project Identifier or feasibility analysis. RETScreen actually is a tool that is developed by Natural Resources Canada, CanMed Energy, but with support from many other agencies, including an agency that's supporting us here today, Save on Energy, and the Independent Electricity System Operator in Ontario. Many of you, if you've used RETScreen, know that NASA does provide functional support too, in the sense that a lot of weather data, which we may use in other aspects of RETScreen performance analysis, comes from a cloud, essentially a cloud database. So it makes it really easy to get the information you need to do the analysis that you're doing. So suffice it to say, it's supported by many entities. And as I said, it's a tool. It's all in one toolbox. I did an introductory workshop the other day. Folks were looking at it. They've never used it before. They were using a whole range of spreadsheets to do all the different things that they needed to do in energy. And what they realized, what RETScreen basically covered about 95% of what they needed. So sometimes you need to supplement with a small spreadsheet calculation or a small hand calculation, but RETScreen largely has what you need. And even when you have to substitute, actually, Michelle will show this today. Um, there is in the reheat calculation of RETScreen, we're actually going to show you a way to enhance the calculation that's done by using another function of RETScreen and a small hand calculation. So, there are ways to do pretty much everything you need to do in RETScreen. And the other thing I always say too is, if there's something that's not there, send the folks at RETScreen an email. From time to time, things pop up, and I go, "Where'd that come from?" They said, "Oh, well, somebody requested that." So, they are very responsive to the needs of the user. So, and you potentially are going to be future users. So, they're always looking for that feedback. So, RETScreen also has a lot of support. So if you're looking, and here's an example, if you're looking at a variable speed drive and you want to know how would RETScreen answer solve the problem or give me some solution to a variable speed drive application on a fan. Well, you can go to the case studies and templates, which are accessed from actually from the front page on the lower, in the second column, the lower left-hand side. And if you go into case studies and templates, you will actually find, I don't know, hundreds of different circumstances, either case studies, which are real problems, which are being solved with RETScreen, or templates, which are sort of hypothetical situations solved with RETScreen. One way or the other, it's a great teaching tool, self-teaching tool for yourself. In addition to that, there is within the software contextual help. So whenever you're in there, say you're looking at a fan system and you're wondering what they're talking about, well, if you roll over the label, you'll get the textual help there within context. But the top of most of these dialogues, there's also an e-learning button which you can hit, and it'll take you directly to the YouTube or RETScreen's YouTube e-learning site with typically a video for that particular circumstance that you're in. So there's lots of online help available. Actually, the final thing I'm going to mention is I always tell people a really good starting point is the virtual energy analyzer. So if you click into that, you can basically find many, many different projects. And again, they're all solutions, right? There can be low carbon or low energy projects. They can be a building-wide type of project, so you could pick a type of building, or there could be a particular system that you might be looking at. So lots of resources. So two of them that I just mentioned here, the virtual energy analyzer and the case studies and templates. Good ways to go and learn about how RETScreen could be used in different circumstances. And then don't forget the videos that are available, which will help you. Many people say these are really useful. The nice thing about the videos, you can kind of play it and you can follow through what I'm in some of the videos, what I'm doing on the screen on your version, and then play with it that way. So it's quite useful. All right. So let's talk about modeling a basic HVAC system in RETScreen. So I think I've picked a constant volume system here, in a sense a rooftop unit. Well, there's a lot of stuff in here, right? There's a lot of screens here, and what we want to kind of do is throw everything at you. I'm actually going to jump over to slide 12 and show you the system that I'm actually modeling here. So here we have a rooftop unit that provides heating and cooling. Return that comes back from the space. It's maybe mixed with some or you ventilate, or you exhaust air that you don't need. You bring in outside air, right? You create mixed air, and that mixed air then is taken and heated and or cooled depending on what's required, and then discharged to the space. So that's the rooftop unit that we're actually modeling. That's the system that we're going to model in this simple example. In order to do that, I'm going to need a number of different models in RETScreen, a number of different aspects of RETScreen. I'm going to need a heating system model because I have to take the natural gas to that rooftop unit and combust it and create heat with it, or raise heat with it. I have to have a cooling system. I have to be able to use electricity to raise cooling capacity within the system. I need a ventilation model, right? I need to be able to deal with how the air is heated and cooled coming into the building. I may actually need a model for the fan, right? I may need, if I have, depending on what I have in the building, I may have an exhaust system, in which case I can use a simpler ventilation model. So there's a number of different models being used in this circumstance. What I'm The other thing that when we're talking about these types of systems in RETScreen, um, and this is something you're going to have to take back and think about, right? This is not something you can look at right now and go, oh, I get this right away. But it's important within RETScreen, and we'll use this terminology throughout this session today, but also through the session in a couple of weeks' time, the idea of fuel and energy. In RETScreen, fuel refers to whatever you purchased. So in fact, fuel also refers to electricity in RETScreen's terminology. So you purchase fuel, right, in the form of electricity, right, to create light, right, in a space. You actually purchase natural gas, let's say, as a fuel, and you take that into the heating system and you convert that natural gas to heat, and you lose a little bit of energy, right, up your flue or your vent when you do that conversion process. And the same thing in the cooling system. We use electricity to create cooling capacity, right? And we reject heat, right, from that system. So we need to know, in terms of the heating and cooling systems, their ability to convert the heat, how well they convert the fuel to heat, which is the efficiency of the heating system, or how well they convert the electricity to cooling capacity, which we refer to as the coefficient of performance. So the other thing that RETScreen does, and we'll focus a lot more on this one next week or next session, but RETScreen actually conducts what we call an energy balance on a conditioned space within the building. So it looks at all the heat going into that space, which could be coming from people, it could be coming from lights, it could be coming in the windows, right, in the summer, and then it looks at the cooling required to cool that space. It also looks at the heat required to heat that space, looking at the net flow of heat through ventilation, through windows, through the walls, and then actually the heat coming in from lighting, right, which actually manifests itself as heat in the space and helps to displace a little bit of the heating energy required. So energy in RETScreen is what delivers to the end use. We have an end use function, and we'll be looking at the end use models. Fuel is what we purchase, and then we convert to heating or cooling energy in the heating cooling systems. So there's our rooftop unit. We've got our heating and cooling coils, or basically units within the rooftop unit, probably a DX system for cooling, and probably a gas-fired, indirect gas-fired system for heating purposes. So we need to do is specify what that looks like. So we need to specify the electricity and fuels that we're purchasing. We need to specify the schedules, the temperatures, and the times that we're actually running this system. We need to specify what the heating and cooling system looks like, in a sense, the efficiencies and the COPs, and then we have to specify how we ventilate, and then the fan that might be moving it. So we need a number of different elements. We can't just go and pull a rooftop unit and say, there it all is. No, we have to basically specify each of the different elements in RETScreen. So this will be the exercise that we do in the next session. I think we'll take every one of you through at least one of these exercises. So we're going to be working with a piece of heating equipment that's 80% efficient on a seasonal basis of converting natural gas to heat, a piece of cooling equipment, right, which could be a DX or a compressor unit with a seasonal coefficient of performance of 3. Then we're basically cooling a building to 21 degrees as well as heating it to 21. We have the full fresh air or full capacity of that system being 5,000 CFM, and we're bringing in 20% of outside air. We have a 5 horsepower motor that we've measured as using 3.5 kilowatts, right? It is actually drawing or running the system itself. It's moving the air. And then the ventilation system operates 24 hours, 7 days a week, which is probably not ideal, but there's an opportunity in this system. We can specify the damper leakage. In this case, it's medium, and the system does not have heat recovery. And what we're going to do in the proposed case is to change the schedules to bring the operating schedule of this rooftop unit closer to what's required for the people in the building. We're going to implement a setback and setups of temperatures. And we're going to do all this for a relatively low amount of energy, a little bit of controls upgrade of about $3,000. So we can roll all this together. So we're going to need a schedule, heating equipment, cooling equipment, ventilation equipment, and a fan motor to deal with the entire system. So the results look like this, but what I'm going to do just for a couple of minutes here is I'm going to jump into RETScreen and just show you what this looks like if we're in RETScreen. So in RETScreen, I start off with my main screen, go to home here, right? I have my location, which is where I specify where this system is. So we're going to assume that the system is operating within Toronto. And here we have climate data for Toronto. So all the information we need to determine essentially the impact of the outside environment on this system. We have a facility where we can do some benchmarking. We're not going to touch on that today, but we are going to go to the energy model, and we're going to look at all the different models that I've had to create in order to model the situation. So you can usually follow across the top here in terms of using RETScreen, but I'm going to follow down the left-hand side here, the little tree on the left side. We'll take a look at all the different elements. So we have electricity and fuels. This is where we specify the fuels that we're using, electricity, and the prices. Then we have schedules. So here we have a 24/7 schedule, which is what we have in our existing situation, and our proposed situation will have a setback schedule. We have a heating system. The heating system has an efficiency of 80% in both what we call the base case and the proposed case, the way it is now, the way we want it to be, right? So we're not going to change the efficiency of the heating system in this example. We're simply going to change the operational parameters under which it's operating, temperatures and schedules. We have a cooling system. Here we see the coefficient of performance of the cooling system, right, is 3. That's the only number we really need in RETScreen to specify a cooling system. Don't be tempted to use the capacities or the refrigerants in the cooling system. Those are great functions for recording this information within your project file, but the minimum information required for calculation of RETScreen is going to be the coefficient of performance. So that's one of the neat features of RETScreen, is it doesn't require a ton of information to get an answer out. But you've got to have that number reasonably well specified in order to get a reasonable answer. Now, so that's basically what it takes to get heating and cooling energy to the end use. So we have end use, which is in this case, a constant volume system. I'm not going to go through how this one works here right now, because Michelle will actually go through this in a few minutes. But basically here we have a constant volume system. We can specify the overall airflow, the schedule that it's operating under, how much fresh air on average is brought into the system, whether there's reheat. Michelle's going to refer to that one later, and then how we're actually scheduling this unit for control. Right? And eventually it tells us at the bottom, this is the amount of heating and cooling energy we require in our base case. Right? And then it'll do the same thing for the proposed case, heating and cooling energy required. We go to our fan. So here we specify, the way I've specified it here is as a very simple electrical load, right? I call it the rooftop unit fan motor. And here I've got the measured load, 3.5 kilowatts, operating for 160 hours. In our proposed case, we've reduced the hours. So that's how we specify this system. And what the results look like are over here. Now, the only thing I have in this one, which is actually in addition to what we actually will use in our example next week, is a washer and exhaust fan, but let's just ignore that for a moment. So what we see here then is RETScreen tells us that the fuel saved, that's what we're purchasing, the fuel saved, right, totals 3,419 kilowatt hours of heating fuel and 1,540 kilowatt hours of cooling, right? The electricity not used is 19,000. So that's basically turning the fan off. And this is the heat, right, not used by over-ventilating the building during the unoccupied periods. Now, we can examine in the screen here the fuel used in the base case, the way it is now. So it shows us all the fuel used to heat and cool the building and to run the motor. We can look at the proposed case, right? And then the difference between those two obviously becomes the fuel saved. Now, the one question I often get in RETScreen, people say, well, if I go into the any one of these end uses and I look at the heating and cooling energy down here, 42,933 and 7185, and I go back out to this results screen, right? These numbers don't match. Wait a second, the ventilation requires 34 and 1540. Why don't these numbers? Well, first of all, we have to specify the base case, because that's what we're looking at, but even these numbers don't match. Well, that's because these are fuel, right? Fuel is converted to energy, right? And energy is what's reported on this screen down here. This is energy. That's the end use energy. So in order to make those match, we have to change the view to include base case energy. And when we do that, the 42,933 and 17 to change now match. So using these tools in RETScreen, you have to be a little careful of those settings to make sure you're actually displaying and comparing apples to apples. It all works, but you just have to take a little bit of care. So next week we'll spend a bit of time working on that hands-on. So the overall result of this system, right, and I'll just go back to my slide deck here, the overall result here in this situation is that we made some changes and we have a 0.8-year simple payback. And basically these changes are simple controls changes, maybe in addition of a sensor or a relay or something like that in order to affect the control, but relatively quick savings. And that's what we typically find from operational improvements or controls adjustments within an HVAC system. Michelle's going to dig a little deeper now into some of the different circumstances. Michelle, anything you want to add there?
No, I think that's a good summary. I did add something in the chat. I said electricity is a fuel. When you look at fuel, think, energy consumption. That means electricity is a fuel.
Yeah, that's the part that you really have to keep your mind around, right? So even though it says electricity and fuels here, when it comes to the table, which is what we call the include table, which is the results, right? What we see in here, so fuel consumption based case, this is electricity here. This is electricity here. So yeah, we just have to keep your mind around it. And I'm gonna also I'll come back to the slide that we had here a little earlier, they're very confusing. Well, it's not confusing, but it does look confusing to begin with. But it's actually a very important diagram to understand how RETScreen does its energy accounting internally, right? So it has this condition-space boundary. And that actually allows you to consider the effect of a lighting retrofit on heating cooling systems as well. So it's actually a very important feature of RETScreen. So it's worth taking a bit of time to looking at this and understanding what it's saying. Michelle, over to you.
Thank you, Stephen. All right, so I'm just going to share my screen. It'll take a second. There, we should be all set. Are we all set, Stephen?
Yeah, I think so. Yeah. So what Michelle's going to do is kind of run us through the different situations. But next week you're going to run through yourself. So it'll be a duplication, but hopefully through that you'll actually learn how to use these features.
And the first thing I'd like to mention, Stephen, is what you just showed us is what RETScreen is really built for. It's what you have modeled in there, what we saw, and what you guys are going to model the next time is a single zone system. Basically, your typical rooftop unit. So that means that when you model that, RETScreen considered that the system is able to provide both heating and cooling, which is a switchover system. And you might be wondering, where am I going with this? You'll see in the next slide. It is quite important to know your system. So RETScreen, in the configuration that Stephen has showed us, is modeling a single zone rooftop unit, so switchover system. Kind of a little warning is that the actual economizer operation is not considered, and it's not a big deal, but you should know that the free cooling aspect is not explicitly modeled in RETScreen. So where I was going with that is before you start modeling anything in RETScreen, you have to think, what kind of system do I have? It is critically important, and I cannot stress that enough, that you understand the type of system you're going to model. And when I say that, you always should go back to the basic and say, what is my system providing to my building? And you might say, well, it's providing heating and cooling and ventilation and filtration and humidification. But I would say, you know what? Hold on here. Are you sure that it is providing those services to the spaces? And I'll show you a number of examples where it is not the case, where a system provides ventilation but does not provide space heating and cooling, even if it has a heating coil and a cooling coil. So you look at what I call the 5 basic services. There are some other ones that are possible, but let's say those are the most common services provided by an HVAC system and an air handling unit to the space. And I'm very careful to the space. And always look at that, look at what you're going to try to model in RETScreen, and that will dictate how you should be modeling it in RETScreen. Stephen showed us how we approach the single zone system, and actually I'll go back over that. But we'll look at actually 5 systems. Stephen's going to present us a kind of a case study for the last one. But I'll go through 4 different scenarios. And I could actually ask you guys when we get to that screen, I'm going to ask you to tell me how many services are provided. Is it like the single zone system, or is it more or less services than the single zone system? So let's start with our first one. So the first scenario we're going to look at, a system that you guys are going to have to model in RETScreen in your, if you have to do a building model, is such a common system. So you'll look at this system. Makeup air unit. Out of curiosity, if you have access to your chat, how many of the 5 services does a makeup air unit provide? Just give me a number between 1 and 5, just out of curiosity. Does it provide all 5 services or less than the 5 services that you saw in the previous slide? I'll see if nobody chimes in, Stephen, I'll keep going. So we have 2. Jamie, tell us 2, which is actually very, very close to what I was going to say. So if you think that this system provides heating to the space, that is typically, you always have to be careful, it's typically incorrect. That system is almost a pure ventilation system that provides fresh air to the spaces, I should say outside air to the spaces. It should rarely be used as a heating system. It should rarely be used as the main cooling system. It does cool the air, it does preheat the air, but that's not for space heating or space cooling purposes. It's for conditioning of the ventilation air. Doesn't do filtration of the space air either, nor does it do usually a lot of that. It does humidify the air, but not necessarily the space. If you get infiltration, you will need additional humidification. So between 1 and 2, if you include humidification, and where it's going to be important is that this system, which is basically a ventilation-only system, is a makeup air unit, precondition the outside air, but does not provide space heating and cooling. So it's what we usually call a cold deck system. The reason they call that a cold deck system, as the little pop-up green box says there, is that this system typically is controlled to maintain a supply temperature that will be at or below the space temperature set point. And usually it's below the space temperature set point. So it's not what we call a switchover system. It will not provide heating. And I told you, in RETScreen, by default, the system is designed to be heating and cooling, but there's ways to work around that. It's not actually that difficult, and that's what we're going to work on probably in part next week, but I'll show you also in the next slide. So remember, it's a cold deck system for the majority of those systems. And how usually do you know that it's a cold deck system? The easiest way is to know how are the coils of the unit controlled. So if I go back to that slide, those coils, let's assume one is a cooling coil, even though both are shown as a heating coil and a preheat coil. Let's assume it's a cooling coil, one of the two. The thermostat controlling those coils would not be in a space. A cold deck system has a thermostat located in the supply duct. So if you have a system that is controlled by a supply duct sensor, you will have to model it differently than you would do with the single zone system that we saw in RETScreen. So that's actually, I cannot, again, underline enough how important it is for you to understand if you have a cold deck system, so a system control by a supply temperature sensor. And again, there are exceptions where you do have a temperature sensor in the supply duct and it's a switchover system, but I'm not going to go there, Stephen. I know probably I'm going too far already. So when you have a makeup air unit and you want to define it in RETScreen, there's actually 2 ways you can do it. You can use the screen that Stephen showed us before, which we call method 1. You see on the screen here, it says method 1. So if you use method 1 right here, you'll have that same screen where you can define, the percentage of outside air, the flow of the system. But you can also use method 2 because it is by default 100% system. And method 2 is for systems that are 100% outside air. That's also where you would define exhaust. And I will talk about that. So for a makeup air unit, you could actually give it a name. I forgot to give it a name here. You would define if it's heating or cooling. So it does address one of the question I said, if you have heating only or cooling only, it's pretty simple. Then you will assign it a schedule, and I'm going to talk about that schedule. That is where the critical point will be when defining a makeup air unit, and obviously it's flow and heat recovery. It does by default, if you put the heat recovery, assume that there is an exhaust fan that will make up the same amount of air so that you have that balanced flow. So the heat recovery that you have in RETScreen will be a balanced flow heat recovery. And you do not define the exhaust flow. By default, the exhaust flow will be balanced to the makeup flow. So don't define both, only define one. Now, This system in RETScreen by default is controlled by a space temperature sensor because the system is designed to do that. That's how RETScreen is programmed. But you don't necessarily have that. If you have a cold deck system with a duct sensor, then you have to define a schedule, because the schedule, as we'll see, and Stephen, I can show it if you, actually, I do have it on the next screen, so I'll show you in the next screen. Schedule defines not only the hours of operation of the system, but also the temperature. And in this case, the makeup air unit is not trying to maintain the space temperature. That is usually done by baseboards or other equipment. So in this case, you have to define a schedule that has a temperature that actually is dedicated to the makeup air unit. So that's where it's going to make a big difference in your results. So the way you would do that is, we'll see that you define the schedules in RETScreen. There's always a default schedule that's 24/7 where you can have a set point. And actually, I'm going to zoom on this here. And when you have a makeup air unit, I'm not going to go into the details, the calculations details for that, but your supply set point need to be a couple degrees higher than your space temperature set point. I mean, we can address the reason why later on if need be, but just, know that if you want a proper makeup air unit calculation, if your makeup air unit is to supply at between 18 and 20 degrees to a space that's kept at 22, you would need to define a schedule that has a different space temperature, and that would be a couple degrees higher. So that's how you would define this cold deck system in RETScreen. It may be counterintuitive, saying, hey, I'm defining it with a temperature higher than the actual supply temperature. Yes, that's true because of the way the whole load calculation is done behind the scene in RETScreen. So that's going to be important. If you define it exactly at your space temperature, is not a huge error. It will underestimate your savings. If you put heat recovery or demand control ventilation, you will get slightly less savings than if you would use the rule that is, or the guideline, I should not say it's not a rule by any means, that is shown here. So basically, that's how you would go for a cold deck makeup air unit. Now, if you only have exhaust, if you have exhaust only, you don't have a makeup system, then let's go back here, and an exhaust fan would be defined the same way, but you do not have to define a different schedule, because now this exhaust fan, which is not linked to a makeup air unit because the building just goes negative pressure, that exhaust fan, its actual heating required to, through infiltration to make up the heating and cooling required for that air that's exhausted, is done by the baseboard, is done by the building heating system. Therefore, it is subject to the actual building heating and cooling schedule. So if it's an exhaust-only system, not linked to a makeup air unit, then you define only the exhaust. And always remember, the one thing we see quite often, Stephen, is people trying to define both the makeup and the exhaust. So they end up doing double accounting of the outside airflow, because RETScreen won't make the link that this exhaust and that makeup air unit is the same outside air, and you will end up with twice the energy use as if you were defining it properly.
That's really important, because RETScreen, the best way to think about RETScreen is as an accounting program. It accounts for the energy flows. And once you've accounted for air coming into the building and being heated, that actually implicitly accounts for the fact that you've got to take outside air or inside air and reject it. So basically, yeah, one or the other, but not both.
Not both. So that's, I'd say, the big caution about the makeup air unit is, if it's a makeup air unit that's cold deck, use a different temperature schedule if you want proper load calculation, or a more realistic. Not that the other one's bad, like I said, it will be a conservative. Now we're going to go to the single zone system. That's the one that Stephen showed us, this constant volume single zone system. I'm not even going to ask you how many services it provides. I think I probably gave you the answer before. It provides all the services. All 5 services are provided by this system. Actually, this system is the basis of the method 1 system that we see in RETScreen. So if I don't know, sorry, went on the wrong way. So if I go back to this screenshot, which is how you're going to define your HVAC system in RETScreen, what you see here, so this is actually method 1. So method 1, which you can use for a makeup air unit, nothing prevents you from doing it, but it's definitely the one method you need to use anytime you have a mixed air system. So in this case, the mixed air system is single zone. So it's switch over. It goes from heating to cooling, just like a residential furnace. In this case, it's a very straightforward definition of all of those components. The schedule, well, right now I've got a 24/7 schedule in the base case. And as Stephen said before, we can define a proposed case with measures. It will actually be the space temperature set point that you actually want to maintain in the building. And if you have a setback, it will actually include that in the schedule that I showed you before. Then you will enter the percentage of outside air, which here is called fresh air. I stay away from fresh air usually because depending where you're located, the outside air is not always that fresh. So the percentage of fresh air. And then there are a number of other selections that are made, one for system reheat. Now, if you're single zone, you do not have reheat. So you will not select reheat for a single zone system, such as lots of small rooftop. So don't select reheat. And obviously after that, you would define if your system is running all the time. By the way, the difference between ventilation and intake air damper is if you have an outside air schedule compared to a fan schedule. So one is fan schedule and the other one is outside air schedule. Usually we will have them as scheduled, and it will then follow whatever schedule you define in your schedule. If you have heat recovery, you will define it here. So this is straightforward single zone system. You don't really have any, I'd say, workaround. So the system provides all 5 services: heating, cooling, humidification, filtration, and ventilation. So nothing other to do than properly enter what really represent your system. So this is probably the easiest system that can be defined in RETScreen. A few words of warning here. That system, when you define it, make sure that the coils are controlled by a space thermostat. If it's not, you don't have a single zone system. It's running as a cold deck system. So always refer back what is controlling the coils in my air handling unit. If it's a space thermostat, then you're good to go with the current schedule you have. Remember, the free cooling is not considered, and this one goes back to what Stephen just mentioned before. If you've got exhaust flows, and those exhaust flows are compensated by the minimum outside air of your system, don't define the exhaust again in terms of airflow. Just define the exhaust in terms of the fan motors. And Stephen will see next week how we define the fan motors. It's a different element, as you mentioned earlier today. But be careful. Otherwise, you will double account again for that same exhaust flow, which may just be compensated by the minimum outside air or the percentage of outside air that you define for your fan system. So quite important to do that. The next one is a little trickier. So the next one you can often see is a constant volume system with reheat. Those systems present in older building are cold deck system. They are not hot deck system. So they don't provide all 5 services. They do not provide space heating unless it's a switchover system. And again, I'm not going to go into details of those systems, but they are not that common. Usually, if you've got a lot of zones with reheat coils, your heating and your cooling coil will be controlled by a duct sensor, which makes it a cold deck system. Now you could say, how am I going to define that? Just like a makeup air unit? And the answer is no, not at all, because this one, unlike the makeup air unit, has a recirculating damper. So you will use that same method as we saw before, this one here, but you will have to define a different type of schedule for this system. A bit like we did for the makeup air unit, you will have to assign a specific schedule as soon as you get this cold deck multi-zone system. Now, this one has reheat coil. You could be tempted to go in here, and I'm going to zoom in here and say, I'm going to use this reheat. I'm going to use system reheat. And I would recommend not to do that. We have developed a more accurate way of doing it, or more flexible, I should say, maybe not more accurate, but definitely more flexible. So I would say for now, stay away from using that system reheat. If you want to model your reheat properly, more, let's say, flexibly, we have a method that I'll show you in a second. So
Michelle,
you will,
people
yep,
often ask me the question, okay, if I specify system reheat, how much reheat am I getting? And that's the problem. RETScreen does include a certain amount of reheat when you turn that switch on, but it's kind of a
yeah,
predefined amount, and
yes.
it works reasonably well. But Michelle likes to be a little more specific, so he's going to show you a method where you can actually specify the amount of reheat and add that in separately. So that's one of
Yeah.
the features of RETScreen. When it doesn't quite do what you want it to do, there's always a neat way to work around it. Go ahead,
Yes.
Michelle.
Yeah, you're absolutely right. Thank you, Stephen. Like I said, it does account for it, but if you want to do a model that will be more closer to what your reheat is, you'll be better off using what we're going to show you in an instant. So, words of caution, I already told you this is a cold deck, so you're going to use a specific type of schedule for that system. The reheat will define as what we call a process load, because reheat really is not dependent on outside air temperature, because your supply is going to be at a given temperature. Let's say on average, let's say it's 18 degrees. Your space is going to be at 22. So basically, your reheat is that delta T, that temperature differential, times a number of hours and times the amount of flow that goes through those reheat coils, which will have to be estimated by, obviously, the energy modeler. So, and you have to be also aware that when you have a multi-zone system in RETScreen, it is not assigned to a specific zone. That's why the system cannot be controlled by a zone. There's no link between a given zone and the system in RETScreen. And that's why you will use this approach to define a different schedule. So when you define a schedule, and I'll show you that in the next slide, for a cold deck multiple zone system, you would enter the heating set point at either 5 degrees minimum or 1 degrees above the yearly average. RETScreen always shows you the weather data for the location you have. It has a column that has the outside air temperature, and at the bottom of it, it gives you the yearly average. So you should define 1 degree above that yearly average, or never go below 5 degrees. So it will be 5 degrees C or 1 degree above. And again, we could go into a lot of details as to why do this, but just remember, a cold deck system is not a heating system. A lot of its heating is done through the return air and not through the heating coil. A lot of VAVs in warmer locations like Toronto and Montreal, they don't even have a heating coil very often, because they need so little heat because of a lot of that return air. So that's why you have to define a different schedule. For the reheat, like I said, I recommend not using the default value, but you would use your system flow. Let's say you got a 10,000 CFM system, and usually this room temperature minus supply temperature will be about 22 degrees minus 18 degrees Celsius times 9/5 to go with Fahrenheit. Times the percentage that you think that total flow will result in reheat. Usually it will be between 10 and 30% that will be, reheated because of those reheat coils. So then you would define in RETScreen, and I'm going to zoom on that, you would define a process load that has the calculation. In this case, I put it in kilowatts. So the equation you see will give you in BTU hours, converted that in kilowatt. And then you'll say how long this reheat will run in terms of hours per year. And that will allow you to capture your reheat in a more flexible manner. Now,
So
the
just actually,
VAV,
just to
yep,
review that, Michelle, the
yep,
flexibility you get is you get to set the supply air temperature, you
yes,
get to set the percentage of airflow that's reheated, and you get to
absolutely,
percent the time as well. So you have
exactly.
three things you can control.
Uh,
But you've
yeah.
got the calculation tool in here to do that.
Absolutely, you do. And for the schedule, forget it says VAV here, but it applies both to VAV and constant volume, because those two systems are cold deck system. You see that my supply temperature is set at 8.2 degrees Celsius. It could have been 5, but my average space temperature that was for Toronto was 7.2. So the rule is 1 degree above the average or 5 degrees, whatever is the highest. And in this case, it was 8.2. Believe me, this has such a large impact on the results of your model that you do not want to miss on defining that. If you miss that and you forget about it and you define a constant volume reheat or VAV with, let's say, this schedule instead, the 24/7 schedule, and you installed a heat recovery in the system, your results can be really, really different. So you got to be very careful about that. So cold deck system would be defined like that. The last one I'm going to do, I'm going to go quite, I'm going to say fast. I don't want to go too fast, but it's pretty much the same as the previous one, except that there are VAV boxes. So your standard VAV system, it's a cold deck system almost all the time, other than the few exceptions where it is a switchover, which is pretty rare. So it has a sensor right here that will control the coils. The only difference compared to the previous one is you probably have minimal reheat. You may have some reheat, but it's minimal, but your flow will vary. So in your definition of the system, where you have to enter the flow, you will have to enter your estimate of the average flow. But it's similar service. 4 of the 5 services are provided by this system. It is not a space heating system in most cases. It is a cold deck system. And you may have reheat coils, but it's usually not the primary source of space heating. It's usually used maybe with fan-powered boxes, so it's more minimal, but you can still do the same approach for reheat calculation that we discussed that has flexibility. And when you define the system, again, you will go in RETScreen. Compared to the previous system, the constant volume, like I said, it's the liter per second or CFM. Here, you would not enter the nominal flow. You would enter what you estimate to be the average yearly flow. The percentage of outside air, just a quick word, if you see on your BAS 15%, take that with a grain of salt. That may not be your true percentage of outside air. Dampers are not linear, so if you can get a better estimate than the percentage you see on the BAS, that'd be great. And then, like I said, the schedule is defined to that VAV schedule. Very, very, very important. The other elements, very similar to what we saw. And basically, that becomes your VAV system. So the cautions here, I just mentioned it. The flow modulation per se is not modeled, so it's for you to enter the average yearly flow. Make sure that if it's a cold deck, which is likely going to be the case, you have this schedule. And if possible, if there is reheat, I would not use the reheat, but use the process load that the method we just saw before. And that brings me to the last scenario that, Stephen, I'm going to let you take over on this one.
I got you there. Thank you very much, Michelle. That's great. Good timing. We've got a few minutes left. I'm not seeing any other questions in the chat, but you can check to make sure. So I'm going to finish off with an interesting one. It's a pretty simple system in a sense. It's a situation where you have exhaust, say, from a kitchen or some process, or even general exhaust. But we're going to focus in this example on a kitchen. And one of the big opportunities in this type of circumstance is applying what we call demand control ventilation. That is changing the ventilation rate depending on what's required. You know, oftentimes we see kitchens that are running, you know, it could be full volume, you know, a constant volume system for maybe 8, 10, 12 hours a day. Sometimes they run the whole day, right? So what we're going to do here is model a circumstance where we're actually taking a system that's running full volume 24/7, and we're going to then basically bring it down to a certain percentage of the volume for certain hours of the day in response to a demand. Now, RETScreen doesn't actually have a model for demand control ventilation, but you can very quickly use the models that we have for this purpose. Now, the one thing to keep in mind in this case, often the air that's being exhausted here, where does it start out in the building? Well, it starts from the rest of the building. It's conditioned basically within the rest of the building, unless there's such a thing as a direct air makeup to the kitchen. But what I'm going to model here is a situation where we have a building where the air is drawn from other parts of the building. So it's heated and cooled, right, before it then entrains the, you know, the hot, moist, fat-laden air and goes out. So the temperatures that we're going to use here are not the exhaust temperatures. They're going to be the building temperatures, right? Because that exhaust heat that we're getting rid of, that's simply just lost, right? I mean, that's not the air that we're paying to heat. We have to heat that air or create that heat over the stove for cooking purposes, we would account for that differently. But what we want to do is account for essentially the makeup air that's coming through the building and being entrained and being exhausted by this hood. So in the base case situation here, we have a circumstance where this hood is running 24/7, 10,000 CFM, full flow. And what we're going to do is we're going to go down to 6 hours per day at full flow, because that's what's required for cooking. Let's say they have 2 cooking sessions in the morning and the afternoon, something like that. So 6 hours per day at full flow. And in reality, this might be implemented by a completely variable system. It's not going to be a 2-speed fan or something like that, on, off. It could be on, off, and then lower speed. So you could have a 3-speed situation, but typically today, Michelle, this would be implemented with a variable speed drive and a sensor of some form over in the stove area. So you're basically modulating, but we're going to approximate what that modulation looks like with 3 different modes. 6 hours a day, full flow, 10,000 CFM, 12 hours a day at quarter flow, right? So that's when, you've got other things going on in the kitchen and maybe a couple things being cooked. You don't need the full flow. And then 6 hours a day, say from midnight to 6 a.m. or maybe 10 a.m. to 4 a.m. because the kitchen that cooks for breakfast probably starts pretty early. So 6 hours a day turned off, right? And it's pretty straightforward, right? We're going to be using the schedule for the building, which would be 24/7, whatever that schedule is. And then we would move over to a schedule which would have the same temperatures, but it would simply be, and I don't have the schedule up here, it would simply be the hours. So we would change the hours in that schedule. Same temperatures being the rest of the building, but the hours per day, 6, 12, and 6, depending on the mode that we're in. And RETScreen then does the calculation, and here we see that it's a 62.5% reduction for implementing that. So a simple way to model demand control ventilation for a kitchen hood. And you could apply the same thing, Michelle, in other types of ventilation systems, but I take this one because it's a common project that people would be looking at today. All right, so go ahead.
I just want to mention that we're going to talk about motor power. This is for the heating, cooling savings. Obviously, motors is a different element that we would treat separately.
That's right. I actually would do the same thing as I did on a previous slide where I had the motor power, and I would just simply have three rows for motor power. We'll take a look at that one next week or next session. And so in this case, you have to model the ventilation component like this, and you have to model the fan that moves the air as a separate component, and you still need your heating, cooling, and your schedules on top of that. So modeling HVAC can be relatively straightforward, but you just have to remember the different pieces and how to use them properly in conjunction with one another. So on that note, just a couple of cautions here. Again, don't model both the exhaust and the makeup. So if I'm looking at the exhaust system, in this case, we're assuming the makeup is coming right from the building. Now, we could change it so that we were providing makeup air, and we would have to change the schedules and the temperature. Maybe we're making up air to the kitchen, right, without any or with a minimum amount of preheat. So we could model that, but we would have to then adjust the temperatures and the schedules according to what Michelle showed us earlier, right? And so even when no makeup air is present, this system is defined as a cold deck system, right? So pretty straightforward. All right.
We do have a question, Stephen. Your balance temperature, the changeover that you have in the schedule, it's often 16, 15, around that. So do you use a specific technique to get that balance point?
Well, that's an interesting question. That's probably one of the sort of the toughest questions in RETScreen to answer, to tell you the truth. So what we're talking about here is this changeover temperature here. So in other parts of RETScreen, you use heating and cooling degree days. And for heating and cooling degree days, you would have a balance point temperature for heating and a balance point temperature for cooling. So like in my house, the balance point temperature for cooling is probably 24, 25 degrees C, which means that below that temperature, I don't need cooling. And my balance point temperature for heating is probably 14 degrees C. Below that temperature, I'm going to need heating. Above it, I don't need it. There's a range in there, like today, where I don't need heating or cooling. So that being said, in the RETScreen feasibility model, we don't have this heating and cooling balance points. We have a point at which the building essentially moves from heating to cooling. This calculation is done, as is implied, if we look at this on a monthly basis, right? So RETScreen does not do the calculation on an hourly or daily basis. It does it on a monthly basis. So in here, the technique I use is I say, okay, how long is my heating with the sort of the heating season plus the shoulder season with the possibility of heating. How long is my cooling season plus a bit of shoulder with the possibility of cooling? So what I'm trying to do is divide the year into two halves, and that's the basis on which I set this value, the 16 degrees. Now, what's the valid range or the safe range over which you can change that? I would say we're looking at a plus or minus 2 or 3 degrees. So I would not try to move that to extremes, right, Michelle? If we move it to extremes, it's going to cause trouble in the way the underlying model works. And the other piece that's connected to that, what's very important here is under location, you could change the heating and cooling degree days in this example. But you need to input heating and cooling degree days for your own site, which are calculated to a balance point of 18 for heating and cooling to 10. And what RETScreen does is it then looks at your changeover temperature and it determines basically a set of heating and cooling degree days in between these two. So it recalculates the degree days based on your changeover temperature. So again, the model for recalculating those degree days only has a limited range of validity. So again, plus or minus maybe 4 degrees. So 12 degrees up to 20 degrees would be a reasonable range in which to set that. And you'll see pretty, if I set this to 12 here, I'm going to get, that looks like half my season is cooling, or roughly. If I go to 20 here, then basically I'm going to get a relatively short, be a month of cooling there. So, that's kind of the range, but the technique I use, and in most cases, I will start out at 16. That's not the default. The default in RETScreen, it's blank. But I would typically start out at 16 as a good starting point, and then basically move back and forth. It's going to depend on where your location is. So in Northern Ontario, where it's a lot cooler for a lot of the year, you'll probably see a different number. Even for 16, you'll see a wider number of, or a larger number of heating days. And that makes sense, right? It kind of makes sense. So start with 16, don't deviate too much from that. And that works in most circumstances.
So there's one more question about how to model in RETScreen a system that is not a cold deck system. So I would assume a switchover type, a furnace type system, with a hydronic system. Let's start with that.
Well, the hydronic system really, if it really depends. So I could change the label on this. Well, I'm going to put it in here. So this would be boiler, right? So I'd be putting a boiler in here, and I'm going to put an 80% efficiency on this, right? In the proposed case. Now, so what's the difference between this heating equipment and this heating equipment? The label, that's it. No difference.
Yeah.
Okay, so RETScreen, to a large extent, doesn't sort of look at the topology and the nature of the equipment that you have. It only looks at the energy implications of the equipment you put in. Now, what are you going to be doing with that? Is that boiler going to be providing space heat? If it's going to be providing space heat, we haven't talked about the space heat, right? Which is overcoming envelope losses, right? We've talked about the heat that's required to overcome the ventilation. That's largely what we've been talking about today. But then I would create a building envelope model. I'm not going to go into the details of it here, where I would specify the characteristics of the building envelope, the schedule I apply that to, and then it determines the amount of heating, cooling, or heating and cooling energy at the bottom, right? So, and that then gets applied. So here I would apply that to the boiler. So I might have, like in this situation, I might have a space that's cooled by the rooftop unit, right? Its ventilation is heated by the rooftop unit, but in this case, the envelope losses are the perimeter radiation, right, which comes from the hydronic, and I would specify the boiler for the heating system here. Now, when it comes to the different elements of depending on where the heat's coming from, is that rooftop unit standalone with its own gas heating, or does it have coils, right, which are fed from the boiler? And that will determine where you assign the source of heat to these particular systems. Michelle?
So in this example, you have a gas-fired rooftop unit that could be single zone, and that gas-fired rooftop unit would preheat the outside air, but would not provide the space heating, which would come from the boiler. Now, if you had a cold deck system, there's no link between the envelope and the ventilation component, regardless of the system. So you definitely would need to have some form of heating system associated with your building envelope, just like the boiler. And in your a ventilation system, you would have a furnace still, but it would be assigned to a VAV schedule rather than a standard, hot deck system schedule.
Yeah. Yeah. So you basically you can assign the different pieces of equipment and then assign it to different end use systems. And the two primary end use systems for heat are going to be ventilation and building envelope.
Do we have time, Megan, for the last question?
Yeah, really quickly. We are coming to the end of our session.
Okay. Stephen, the last one is the energy modeler putting the incremental initial cost and incremental O&M values in the calculation?
Well, down here we have incremental O&M cost, incremental initial costs. What that means is if we have to replace a system anyway, right? Then getting to the proposed situation, right? Do we take the full cost of replacement? Say we're doing this at replacing a rooftop at asset renewal time. Let's say we're going to take a rooftop unit over to an electric one, right? To a heat pump, right? And I'm going to have electricity here. So the question, I'm going to put a COP of say 200%, which is basically, or 200% efficiency with a COP of 2. So what incremental cost do I go in here? If that rooftop unit needs to be replaced, then what I would put in here is the difference between a gas-fired rooftop unit and a heat pump fired or heated rooftop unit. That's the incremental cost. If I'm starting from scratch, then I need to bear the full cost. So the incremental cost would be the full cost. But in the case where it's simply the change going from a like-for-like replacement to a like-for-better, then I would use the incremental price. So it was 50,000 for the rooftop unit and 70,000 for the heat pump. Then I would use 20,000 incremental costs. Those aren't correct values.
And if you think your heat pump's going to cost you more in maintenance, then you put a incremental O&M cost.
That's right.
And it would be negative if you think it's more. It's be positive if you think it's a saving.
Yeah, that's right. The O&M.
The O&M.
And just be careful of the signs if you're worried about this. So incremental O&M savings here, right? So savings are positive, costs are negative in this cell. Sometimes it says incremental O&M costs, in which case savings would be negative and costs would be positive. But just make sure you look at the label on that cell. That's good questions.
Thank you, guys.
All right. So yeah, so next week it's going to be hands-on, literally. So we're going to go through many of these examples hands-on in the software. So make sure you have your, RETScreen installed, or Megan will be sending you that information to make sure that you're all ready to go. And we'll probably send out some worksheets in advance too, right? Which people can use to refer to what we're inputting in the software. Megan, over to you.
Thanks, Stephen. Yes, so make sure you register. I put the link in the chat by November 5th. Make sure that you can receive the temporary key, instructions on how to install RETScreen, and as Stephen said, perhaps some worksheets for you to follow along with. I just wanted to point everyone's attention to the Save on Energy training and support website. We have a lot of resources available there, specifically on the topic of efficient electrification, which is where these RETScreen workshops fall within. If you have any questions, you can reach out to us via email. And we also offer some coaching on some of the toolkit resources, which include RETScreen templates. You can always request some coaching through our post-webinar support intake form. So we do these over the phone, video call, or email, depending on what your inquiry is. We can help with certain project plannings that you're working on. And then on our last slide, it's just our thank you slide, some contact information for Save on Energy, for our team here at Training and Support, social media links, and of course, you can use the QR code to sign up for Save on Energy's quarterly business newsletter. Thanks once again for joining us today, and have a great day.
Thanks, everybody.
Thank you.
Thanks, Juan.
Bye.